Evaluate two-sided limits analytically for complex fractions with remote discontinuities. Alright, so in this section we're going to be talking about evaluating limits of complex fractions. And let's remember that a complex fraction is a fraction inside of another fraction. So let's look at an example of limits with complex fractions. So here we want to evaluate the limit as x approaches 0 of 1 over x plus 3 minus 1/3 all over x. So in this problem we can see that we have two fractions inside of the very large fraction. We have this complex fraction and this complex fraction, and they are inside the entire fraction. Alright, so as usual, we always do want to plug in the x value here to see if we can use direct substitution, so that doesn't change with complex fractions. So we'll go ahead and we'll substitute that in just to see what we get. So we can get 1 over 0 plus 3 minus 1 over 3 all over 0, which can be simplified down to be 1/3 minus 1/3 over 0, or 0 over 0. Now, when we get 0 over 0, we know that we need to factor something out and cancel. But the problem here is that the way that it is currently written, this expression, it's not very evident what we can even factor out, let alone cancel. So we need to rewrite this in a simplified form, which means we need to get rid of the complex fractions in this fraction. Now, there are a number of different ways that you could do this, so if you know a better way or would like to do this differently, please feel free to go ahead. I find it easiest if we identify the denominators of the complex fractions. So we're looking for the denominators in the fraction. What do I mean by that? Well, I mean the x plus 3 and the 3 are our two denominators of the fractions in the fraction. Now, what are we going to do with these denominators? Well, we're going to multiply both the numerator and denominator by the product of those denominators. So we're going to take the x plus 3 times the 3, and we're going to multiply it to the top and the bottom, since that won't actually change the fraction. And by doing this, we will hopefully be able to remove the complex part of the fraction and be left with just a normal fraction. So to do this, we are going to have to distribute the x plus 3 times 3 into the fraction. And when we do that, we're going to get the limit as x approaches 0. And yes, we need to keep writing the limit until we perform the direct substitution. And yes, I know it is a huge pain. Yes, I hate it too. And yes, you have to continue doing it. All right, so again, we're factoring that in. So let's see, we're going to have x plus 3 times 3 over x plus 3 minus x plus 3 times 3 over 3 all over x times x plus 3 times 3. All right, so we factored it in. From here, if we're looking at just the first fraction here, we can see that the numerator and denominator have a factor in common. So therefore, we can cancel that out. If we look at the second fraction, we can also see the numerator and denominator have a factor in common, so we can cancel those out. So what does that leave us with? Well, if we rewrite this, we're going to get the limit as x approaches 0 of 3 minus the quantity x plus 3 all over x times x plus 3 times 3. Now, we do know that since we at first got 0 over 0, we're going to want to factor and cancel something out, which is why I left the denominator in factored form, because eventually I'm going to cancel something out. But first we have to simplify the numerator, and I can do that by distributing the negative, and that's going to leave us with the limit as x approaches 0 of 3 minus x minus 3 all over x times x plus 3 times 3. And then from here, if we simplify the numerator, the positive 3 and the negative 3 are going to cancel out, leaving us with the limit as x approaches 0 of negative x over x times x plus 3 times 3. And we can see yet again, the numerator and the denominator both have a factor in common, so we can cancel out the x's, which is going to leave us with a limit as x approaches 0 of negative 1 over x plus 3 times 3. And now, since we have successfully factored and we have successfully canceled, we can now try direct substitution again, which means we don't have to write the limit anymore. And we can just substitute in the a for the x value, so 0 plus 3 times 3, which is going to be negative 1 over 3 times 3, or negative 1/9 as our answer. So, a whole lot of challenging algebra here, but the direct substitution part at the end, it's the only calculus part, is not that difficult. Let's take a look at another example. Here we have the limit as x approaches 0 of x squared over x plus 3 plus 9 over x minus 3. So here we have a fraction inside of the bigger fraction. And we'll use the same process we did last time. We will take the denominator of the fraction inside the fraction, and we'll multiply both the top and bottom by that denominator, which is x minus 3. And then we are going to factor it in to each of the terms. So this is going to end up being the limit as x approaches 0 of x squared times x minus 3 all over the quantity x minus 3, let's try this again, of x times x minus 3 plus 3 times x minus 3 plus 9 times x minus 3 over x minus 3, and I need to extend my fraction bar because I misjudged. Alright, so looking at what we have, we can see we have an x minus 3 and an x minus 3, so we can cancel that out. And then we can rewrite this as being the limit as x approaches 0 of x squared times the quantity x minus 3 all over x times x minus 3 plus 3 times x minus 3 plus 9. Alright, so from here the numerator appears to be in factored form, so we just have to simplify the denominator. And we can do that by using the distributive property, which is going to give us the limit as x approaches 0 of x squared times x minus 3 all over, let's see, x squared minus 3x plus 3x minus 9 plus 9. Well, we can see the negative 3 and the positive 3 will cancel each other out. The negative 9 and the positive 9 will cancel each other out. And that's going to leave us with the limit as x approaches 0 of x squared times x minus 3 all over x squared. And since we have an x squared on the top and an x squared on the bottom, we can cancel out those two factors. And that's going to leave us with the limit as x approaches 0 of x minus 3. And then we can perform direct substitution, 0 minus 3, giving us a final intended height of negative 3. All right, so let's take a look at one more. And we're going to look at this last one because it just looks very scary. And there is a algebraic technique we need to talk about. Alright, so our last example, we have the limit as x approaches 4 of 1 over x plus 7 minus 1 over 11 all over 1 over x plus 1 minus 1 over 5. So we have 4 different fractions inside of our big fraction. We're going to use the same technique that we have, meaning we're going to take all the denominators and we're going to multiply the top and the bottom by all those denominators. So that's going to be x plus 7 times 11 times x plus 1 times 5. So as you can see, there's going to be a lot of writing here, because we need to multiply it, multiply it, multiply it, multiply it in. So that's going to give us the limit as x approaches 4 of x plus 7 times 11 times x plus 1 times 5 all over x plus 7 minus x plus 7 times 11 times x plus 1 times 5 all over 11. And that's all over. Whew. X plus 7 times 11 times x plus 1 times 5 all over x plus 1 minus x plus 7. Oh my goodness, this is taking forever. All over 5. Whew. All right. Well, now that we've actually distributed it, we can cancel out the factors that the numerator and denominator both have in common. So our first term, they both have an x plus 7. Second term, they both have an 11. Third fraction, they both have an x plus 1. And fourth fraction, they both have a 5. So let's go ahead and simplify this. This is going to give us the limit as x approaches 4 of 11 times x plus 1 times 5 minus x plus 7 times x plus 1 times 5 all over x plus 7 times 11 times 5 minus x plus 7 times 11 times x plus 1. All right, from this step, it's very tempting to go through and simplify both the numerator and denominator by using the distributive property. However, this is where that trick comes into play. Because if we actually would simplify everything down, it's going to become very difficult to factor once it's all multiplied out. So we're going to factor before that. What do I mean by that? Well, if we look at both the top terms have an x plus 1 and a 5. So therefore, we can factor that out. So we'll have an x plus 1 and a 5, and that's going to leave us with an 11 minus x plus 7. All right, well, we can do a similar thing in the denominator. We can see that both terms in the denominator have an x plus 7, and they both have an 11, meaning we can factor those out. All right. Well, at the moment, it doesn't appear as though we can cancel anything yet. But let's look at the insides of what we just factored out. And what do I mean by insides? We're going to look at this guy, and we're going to look at this guy. So we're going to simplify those up here so we don't have to rewrite everything again. So we're going to have 11 minus x plus 7. We can distribute that negative in, so we'll get 11 minus x minus 7. And then we can simplify this to be 4 minus x. And then on the denominator, we'll do a similar thing. We have 5 minus the quantity x plus 1. We can distribute in the negative to get 5 minus x minus 1. And that's going to give us 4 minus x. So now we can replace that. So let's see if I can squeeze this in. This is going to give us the limit as x approaches 4 of x plus 1 times 5 times 4 minus x all over x plus 7 times 11 times 4 minus x. And wouldn't you know it, 4 minus x in the numerator and 4 minus x in the denominator are going to cancel out, leaving us with the limit as x approaches 4 of x plus 1 times 5 all over x plus 7 times 11. And then we can substitute in the 4. I'm going to have to skip a step because I'm running out of room. When we substitute in the 4, we're going to get 5 times 5 all over 12 times 11, giving us an answer of 21 over, oh, wait a second, it's not, it's a lie. Come on, do better math. All right, 5 times 5 all over 11 times 11, which will give us 25 over 121 as a solution. So yes, I wouldn't say there was anything super difficult there, but a whole heck of a lot of algebra, a whole heck of a lot of factoring, and a boatload ton of writing. But there you have it, evaluating limits that involve complex fractions.